This video is rotational translation in polar coordinates. I'm assuming if you're watching this that you know how the equation of a circle works to graph a circle, and that you know a pretty good deal of trigonometry, as you can see, and also that you understand horizontal and vertical translations, and that you know what polar coordinates are, particularly x equals r cosine theta, y equals r sine theta. So I'm starting with the unit circle here, x squared plus y squared equals 1. There it is. And when I switched into green, by the way, I had to write all this out in advance because trying to do this video, it was over the time limit with me talking and writing all this, so hopefully you can follow along. But when I switched into green, all I did is subtract 5 from the x, which caused a horizontal translation. All it does is slide the whole thing over 5 units to the right without changing the shape of it in any way. And what I've done next is I'm going to, well, I've converted it into polar coordinates just using these two identities. Just every time I saw x, I substituted r cosine theta. Every time I saw y, substituted r sine theta. So this is the same equation as this one, it's just now it's in polar coordinates. And what I want to demonstrate to you is if you have an equation in polar coordinates, if you subtract something from theta, just like if you subtract something from x over here, it moves it to the right 5. If you subtract something from theta, then it rotates the whole thing that angle in a counterclockwise direction without changing the shape of it or distance that it is from the origin or the pole, actually as it's called in polar coordinates. So I'm going to take this circle and we're going to subtract something from theta so that it rotates it in a counterclockwise direction. What I'm going to subtract from it, as you can see here, is I called it alpha. It's approximately 53.13 degrees. And I called it alpha so I didn't have to write 53.13 degrees every time. And it's actually this angle in a 3, 4, 5 triangle. This is alpha right here. So I just went through this, by the way, I just squared r cosine theta minus 5. And that's where r squared cosine squared theta minus 10 r cosine theta plus 25 came from. This is this. The first line, when I switched into purple, this is when I'm actually going to do my rotation. We're just going to do a bunch of algebra to simplify this. So every time I saw theta, I put theta minus alpha instead. There's one right there, there's one right there, and also in the sign. And there are some formulas that you know from trigonometry. Cosine of theta minus alpha, that's cosine theta cosine alpha, plus sine theta sine alpha. That happened twice in this equation. One time it's being squared, one time it's not. And the formula for sine of something minus something is sine of the first thing, cosine of the second thing, minus cosine of the first thing, sine of the second thing. So the reason I chose this alpha as my angle for this demonstration is that I know exactly, I have nice values for sine of alpha is 4/5, cosine of alpha is 3/5. These things all come up in this mess right here. So the next line is when we can actually get rid of alpha. It's not in there anymore. We just made these substitutions. Cosine alpha is 3/5. Sine alpha is 4/5. Same substitutions happen in here. And same substitutions happen in here. This next line, 3/5 cosine theta plus 4/5 sine theta squared. Squaring that, you just square it like it's a binomial. 3/5 cosine theta squared is 9/25 cosine squared theta. The middle term, you know, this is a plus b squared is a squared plus 2ab plus b squared. This is 2 times this times this. 3/5 times 4/5 is 12/5. 2 times that is 24/25. And there's a cosine theta and a sine theta in there. And at the end there's 4/5 sine theta squared, which is 16/25 sine squared theta. Distributing the negative 10r through here, negative 10r times 3/5 cosine theta is minus 6r cosine theta. Negative 10r times 4/5 sine theta is negative 8r sine theta. There's plus 25 here. And we also squared this, just like we squared the one over here. And that became 3/5 sine theta is squared is 9/25 sine squared theta. This time you get minus 24/25 cosine theta sine theta in the middle. And at the end, plus 16/25 cosine squared theta. All that. And on this next line, which is the last one that I wrote in advance, we're just distributing the r squared through both of these sets of parentheses. And now I'm ready to start cleaning this up. So I see a 9/25 r squared cosine squared theta Down here, there's also a 16 over 25 r squared cosine squared theta. Those add up to 25 over 25, or just 1 r squared cosine squared theta. This is when it starts to go from worse to better, I guess. Best news of the day, 24 over 25 r squared cosine theta sine theta, and then minus 24 over 25 r squared cosine theta sine theta. Those two are going to cancel out, so I don't have to worry about them. So I have r squared cosine squared theta. I think next I'll put minus 6r cosine theta, so I'm grouping my like trigonometric functions together. Here I have 16 over 25 r squared sine squared theta, and down here is 9 over 25 r squared sine squared theta. Those also add up to 25 over 25, or just 1 times r squared sine squared theta. And then I'll put my minus 8r sine theta next. And then this plus 25 is still here, equals 1. This to me looks like a good time to change from polar coordinates back into rectangular coordinates. R squared cosine squared theta is just x squared. Minus 6r cosine theta, that's minus 6x. Plus r squared sine squared theta, that's y squared. Minus 8r sine theta is minus 8y. And there's plus 25 equals 1. So if you're familiar with how to graph a circle and how to work with the equation of a circle, you know that there's this completing the square aspect. X squared minus 6x, that wants to have a plus 9 on it. And y squared minus 8y, that wants to have a plus 16 on it. Unfortunately, 9 plus 16 is 25, so this 25 that's here, I can just split that into 9 and 25, put the 9 with the x's and the 16 with the y's, and what that turns into is x minus 3 squared plus y minus 4 squared equals 1, which is a circle that's now centered at 3, 4, 3, 4 being right here, and it still has a radius of 1. So let's draw this circle using the circle draw tool to cheat a little bit. So there's the circle, and hopefully this makes sense. Doing a rotational translation, it preserves the whole shape of the figure and the distance that it is from the center. Let's see down here, let's demonstrate that on the graph. So this distance right here from center to center is 5. This distance is still 5 because that's 4 and that's 3. So this is our 3, 4, 5 right triangle. This right here is the angle alpha. That's how much I rotated it by. So I recommend that you try this with some other polar equations, particularly conic sections. Circles are really easy to work with, and some fun things happen with it. So try y equals 1 over x and rotate that by 45 degrees. You can do this with any, it works really well with any conics, like I said, and angles to rotate by. You can use this angle alpha that I used, or its complement. It'll give some interesting results also, or any angle that's a multiple of 30 or 45 degrees. As you can see, you can rotate by any angle as long as you can find the sine and cosine of it. That's what's important. Sometimes the resulting equation might require a computer graphing program to do it, but try it out and see some interesting results. Have fun.